All right. The project is due on Friday. This is the big week, the week you've all been waiting for, or maybe I should say the week you've been waiting until, right? All right. So just to remind you, I have office hours every day this week. And if you need to come see me at a time outside of my office hours, I'll do my best to accommodate you with an appointment. Just let me know and we can try and set something up. I'll do my best to respond by email. I saw I got one project question email earlier today. I just haven't been back in my office since I received it to reply yet. The other thing on your schedule is that homework assignment that I handed out in class previously, homework 14. If you don't have the paper, it's available on MU Online. It's due on Wednesday, so yes. On Friday, the project is due in class. Yeah. Okay, well, today we're going to continue talking about cost estimation, which is just this approach to, at the beginning of a project, trying to decide how much it may cost to conduct and budgeting for those expenses. And the first thing we're going to be talking about today is a phenomenon related to the fact that when you've done things over and over again, you get really good at them. So here's a picture of a garment factory where people can sew clothing a lot faster than you and I could. And a big part of that is just the fact that they do it every day for a long time, and they find ways to become efficient. They may find that maybe cutting the material and then sewing it in and sort of a batch process saves time. They're able to just do the seams a lot more quickly than any of us could. Here's an automotive factory where over years and years of producing cars, they realized that maybe chairs with rollers on them so that the workers could relax and recline as they're working sort of improved the efficiency that they could work. It decreased the number of accidents, and so it's an optimization process at the end of which people become progressively better at doing things. And that's the learning curve idea is a model that kind of tries to put a quantitative approach to that improvement in performance. It's difficult to see, but in the graph here, it's just showing that when you've made your very first unit, whether it's the first car that you're assembling or the first pair of pants that you've sewn, it takes a relatively long time to do that. But then the next time, you save a little bit because of what you learned the first time around. And progressively, you get faster and faster at doing things, but there becomes a diminishing return. You're not going to get as much improvement going from your 20th unit to the 21st unit because you've kind of already found all the low-hanging fruit. And you've made the easy fixes and the quick optimizations, and you're approaching perfection already. So you gradually get less and less of a change over time. So that's the idea of a learning curve. Now, the way that we calculate a learning curve, or sometimes called an experience curve or a manufacturing progress function, here's the formula that's shown on the screen. K is how long it took to make the first one. So the very first time that you solved a Rubik's Cube or sewed a pair of pants or manufactured a car, that's K. And it may be units of time. It could be other units as well, because as you get better at doing things, you may use less materials. It may be that you're using less money. But for today's purposes, we're going to think in terms of time. Now, S is a little bit hard to visualize and understand, but think about when you go from your first unit to your second unit in what you've made. You've effectively doubled how many times you've done that thing as you go from 1 to 2. Or you go from 2 to 4, you've doubled the number of things that you've made. So if you take how much time it takes for your first relative to your second, that ratio of time when you double how many you've made is S. And I'll show you an illustration in just a moment of how you calculate S. It's simply just a ratio. So N, once you've estimated what is S, the ratio of time, You take the logarithm of that factor s and divide it by the log of 2, and then that tells you the exponent n that you should use. And then u is whatever unit number you're on. So if you're trying to predict how long it would take you to make 35 units, on your 35th unit, how much time would it take? Then you would use 35 as the u, n would be the factor that you'd calculated with the log of s function, and then k would be how much time it took you the first time around. So what's in the parentheses here is kind of a ratio that's going to start on 1 when you're working on your first unit, and then it's going to be coming lower than 1. It'll be some decimal between 1 and 0. All right, so let's take this as a first example here. If you require 85 minutes to sew a pair of pants, the first pair of pants, what you should write down in your margins there is that k is 85. Because the definition of k is how many units of input did it take to make your first output. And so here we're saying that the input is time and the output is pants, and so it's 85 for k. Now, it's telling us about the second pair of pants is 76.5 minutes. Now, what we can do with that is we can calculate s, and s is a ratio of the s is the time it took for the second pair of pants, which is 76.5 minutes, divided by the amount of time it took for the first pair of pants, which was 85 minutes. And so that ratio is 0.90. They also happen to tell us how much time for the fourth pair of pants. And so again, we're doubling our productivity when we go from the second to the fourth. Our cumulative level of experience, in other words, has doubled as we went from the second to the fourth. And so we can check the ratio just to make sure that it's consistent from the first to the second, from the second to the fourth. So if we do that, 68.85 minutes versus the second pair of pants, which was 76.5 minutes. Then again, if you put that into your calculator, you'll find that it's 0.90. So our S value is correct at 0.9. So we can now calculate N. N is given as the log of S divided by the log of 2. All right, so the log of 0.9 divided by the log of 2. And if you put that into your calculator, you'll find that the log of 0.9 is 0.045757 with a negative in front of it. And then the log of 2, 0.30103. So N is going to be negative 0.1520. So let's go back to this. Boy, that looks great. Here's our formula. We need to know the amount of time it took for our first pair of pants, which was 85, so that's K. U is whatever unit we're on, and it's asking here, how long will it take to sew your 10th pair of pants? So we're going to let U be 10 for the rest of this formula. Okay, so our formula for the 10th pair of pants, the Z sub 10 means how much time it takes for the 10th pair of pants. We should have K times U to the N power. That is 85 minutes, which was the first, multiplied by U to the N. And it's our 10th pair of pants, and so U is 10, and N, we found from above, is 0.1520. Okay, so that makes this factor equal to 0.70469. So it's obviously going to mean that it takes us less time than the first time we made a pair of pants, where it was 85. And the reduction factor here is 0.705, essentially. So that works out to 59.9 minutes to sew the 10th pair of pants. It also asked us in the previous slide, what's the total time required to sew 10 pair of pants? So cumulative. How many cumulative minutes did it take? And we can solve that using Excel fairly easily. All right. The formula that we're going to be using is here. All right. So let's have here the pair number, where we have our first pair of pants, second pair of pants, and so on down through 10 pairs of pants. We want to know how much time it took to do all 10 of them. All right, and then this is the time in minutes. The first thing that we did was we calculated S. Remember that S was the ratio of doubling. And the information that was given to begin with was it was 85 minutes for our first pair of pants. The second pair was 76.5, and the fourth was 68.85. All right, and so the way that we had calculated S was it was the ratio of these two. So that's where we got the 0.9 from, and then N was the log of S divided by the log of 2. And that's where we got our N. All right, so now we can just apply the formula to all of these pair numbers, and so equals K, which was the first pair of pants, and I'm anchoring that because I always wanted to look in that spot for the first pair of pants time, multiplied by U to the N. U is whatever pair number we're on, and to the power of N, which I'm also anchoring because I always wanted to look in that same spot for the N value. So now I'll know that this formula is correct if I drag it down and I get the same value for the fourth pair that already was given. Okay, so far so good. So I can drag it down through the rest of them, and then what the question is asking is what's the cumulative amount of time? By the way, notice it says 59.9 minutes, which is what we calculated when we did the hand calculations there. So cumulative, I can just do a sum function and highlight all of those cells from the 1st to the 10th. So overall, it'll take about 680 minutes to sew 10 pairs of pants. So that's the learning function. For today's in-class exercise, what I'd like you to do is take a look at this problem. I'll give you the handout here. Let's say that you are trying to solve a Rubik's Cube, and the first time that you did it, you actually forgot to time how long it took you. So you're going to have to kind of think on how to back calculate and make up for the fact that you forgot to calculate your first time. Thankfully, what you do have is you've got the 2nd to the 4th, which represents a doubling, and you've got from the 4th to the 8th, which represents a doubling. So you can still calculate and check the S value that you'll need. And then I think once you have the S value, you should be able to use it to go back and find out, estimate how long it took you for that first try with the Rubik's Cube. All right, so once you have the S value, it should be 0.91 to go from the second to the fourth, or from the fourth to the eighth. And remember that you're talking about a doubling of productivity. So if you're going from the second to the third, you're not doubling how many you've made over the life of whatever it is you're doing. But if you go from the second to the fourth, then you have doubled the number of things that you've done for the output. So that's why we don't just go immediately to the next one after. So once you have S, you can also calculate N. But what about this idea of trying to figure out how long it had taken you for the first item that you forgot to time? Well, in addition to going forward with that S factor, you can always go backwards with it as well. And so we know that it took 24 minutes the second time, but this factor of 0.91 would allow you to estimate how long it took to calculate the first time around. So 26.38 minutes. And if you get that, and U is equal to 100, then it should take about 14.1 minutes once you've practiced 100 times. Now, does real life always follow this model? Of course not. But it is kind of a general tendency that we improve at things over time, and that the first improvement we make is bigger than subsequent improvements. And so that's what this model is trying to capture, is just when you're estimating costs, let's say on a construction site, or writing a program, or inspecting a factory, whatever it is you're doing, the first time it's going to take more time for you to do it. And so as you're estimating the costs of a project, you need to build that experience index into your estimates. All right, so let's think about now a cost index. A cost index is a ratio of costs in the past to costs today. And just as an illustration, I looked up in the past how much it costs to make homes compared to how much it costs to make homes today. And there is the Census Department keeps some statistics that, where can I zoom in? All right. It shows, for example, this index that's shown here in 1964. You can think of that as equivalent to, if the index is set as 100 in 2005, then it would say a house that cost $100,000 in 2005, back in 1964, that house cost $12,400. So there are plenty of houses in Huntington that were built in 1964 and way earlier than that as well. There are loads of houses that are more than 100 years old in town. And so if you think about how much those cost when they were originally constructed, it was very, very low in comparison today. This is showing the annual percent changes for houses over time. And we can even go down to more recent times. 2016 isn't complete yet, so they don't exactly know what that index is going to be. But back in 2015, the average index for the year is 114. So just since 2005 until 2015, in 10 years, housing prices appreciated on average across the country by 14%. Now there was a big downtick during the financial crisis back in 2008, 2009, but then the market has stabilized and somewhat recovered. So that is an index that shows housing prices over time. There are also indices out there that track consumer spending, and they do it by partly looking at what sorts of things people spend money on. And so the Consumer Price Index estimates that people across the country on average spend 13% of their money on food. And they even go so far as to break it down into what types of food. You spend 7% of your overall budget on food at home, the rest of it is food at restaurants, and then they even have it broken down. The food that you buy for your house, some of it is related to flour, breakfast cereal, rice and pasta. So this is a weighting average to try and figure out what percentage of people's money gets spent on certain things. And if we scroll down through it, you can see that they've broken it up in terms of energy. 7% of people's income on average is spent on energy. 79% of the spending is beyond energy and food spending. So commodities, furniture, appliances, and so on. It's kind of interesting just to look at only 3% of spending is on clothing. Of course, that varies by person. 4% approximately of spending is on vehicles and so on. So that is a weighting. And then the overall consumer price index will show you over time how the price of goods has changed. So back in 1913, whatever cost $9.80 then, in 1913, that same basket of goods today would cost $236.92. So prices have definitely gone up a lot due to inflation. Now a cost index will use some sort of a data source, whether it's a construction index or a consumer price index or labor or equipment. There are several different published indices out there available, and it'll try and predict what future costs are likely to be based on how much something cost in the past and then the ratio of what the price was overall in the past to an index of items today. So looking back on that very last information source where it was saying, the cost of something back in what was the first year here? Oh, that's not what I wanted to do. All right, it was this one. We don't know from this table how much a candy bar cost in 1913, but we do know that the index is 9.8. So keep that in mind, 9.8. Today the index is 236.916. And so I can't draw on this, I guess. 9.8 spot will take a moment. All right, so we could estimate the cost of a candy bar. 9.8 is the index back then, and the index today is 236. And so if we know how much a candy bar costs today, let's say a large candy bar would maybe be at the grocery store $1.39, you can find out how much the candy bar cost back then by solving for the cost at the previous time. And so we would find the ratio of those two numbers and multiply it by the $1.39. And just because now my curiosity is piqued, I want to put that into my calculator just to see. According to the index, 139 multiplied by 9.8 divided by 236. All right, so that's 5.8 cents. Pretty cheap. So the idea here is that you may not know the price of every single thing, but you can use this index as a method for estimating. And that's what this second part of today's in-class exercise looks at. Let's say that we have information that a repair garage was built in 2004 and the overall construction cost for that garage was $650,000. We also happen to know that back then the index in 2004 had a couple of components. That 30% of the overall price was spent on labor, 20% was on materials, and 50% was on equipment. So that's a breakdown of where the money went. And we also have the index for each of those items. And we could come up with an overall weighted index as well. So what I'd like you to consider for this is, first of all, calculate a weighted index based on the percent breakdown of costs for 2004. So the index is going to be the percentage multiplied by the number that's there, and then you're going to have to add everything up. So this is going to be 0.3, 0.2, 0.5. Multiply them together and you can find the index for 2004. And take the same approach to find what is the index for 2008 with the given information. And then once you have both of those indices, then you can estimate the cost for constructing the garage in 2008. So it's important to keep in mind that what we're calculating is a weighted index. That even if one of the cost categories goes up a lot, that's only going to have a partial effect on the weighted index because we're also spending money in other categories as well. So if you calculate the index in 2004, it should be 149 versus 178.5 in 2008. And so you can estimate what the cost will be in 2008 because you knew the cost of construction back in the past was $650,000, and then you just take the ratio of the two indices to predict what the cost would be if you were constructing it in 2008. And then if you want to break that down into pieces, then you know that 30% of that cost is expected to go towards labor, 20% towards materials, and half of it towards equipment. So this is a very quick and easy way to predict costs for the future, is to go back through your company's history and find out what was the spending on similar projects, and then look at how costs have changed in each of the cost categories that comprised whatever the money was spent for on that project. All right, that's all the time we got for today. Remember, the big thing on your mind should be the project. It's due in class on Friday, so I'll see you on Wednesday.